So our next topic under the image enhancement is noise filtering. Noise filtering. Okay, filtering. Okay, it comes under image enhancement because the idea, the goal is to alleviate, or in other words, mitigate the effect of noise. Mitigate the effect of noise. So as to enhance the visual appeal of the image. So as to enhance the visual appeal of the image. The visual appeal of the image. Okay, as we all know, right? As we all know, noise plays an important role in the sense that it can actually affect the way, right, you would actually appreciate an image. And there are various kinds of noise. One of the noise that we've already seen is what is called a photon noise, right, which we saw earlier. But there are so many of them, right? And we would like to know what kind of simple algorithms that we can employ in order to be able to alleviate the effect of noise. Okay, that is why it comes under image enhancement, because there is also an objective way of doing it, what is called restoration. And out there, right, we would actually employ a more kind of objective approach in order to reduce the effect of noise. Here, the idea is to simply alleviate, right, use some simple methods in order to be able to alleviate the effect of noise, so as to enhance the visual appeal. Now, what this also means that it comes under enhancement or as kind of a subjective notion, simply because of the fact that some people like to see images with noise. For example, scanning electron microscopy. That if you take an image that you capture out of SEM, then what typically happens is it has inbuilt, it has inherent noise in it, and its natural appeal is lost if you try to filter that noise out. In fact, right, people don't like to see an over-smoothed image. People would rather live with noise rather than over-smooth an image. Okay, so the whole idea behind noise filtering is that there is a kind of a trade-off, because when you say filter, that means you're trying to reduce the effect of noise, and that comes at a cost. Right? That comes at a cost because of the fact that when you do that, you're also going to end up smoothing the image, right? So what level of smoothing is acceptable to what level of noise, right, is something that is totally subjective, which is why this particular aspect of noise filtering comes under image enhancement. Okay, because what you might think is actually reasonably filtered might look like an over filtered or over smoothed image for someone else. They might say that probably you should have left out a little bit of noise, and even though right, you may not like to have noise, but some people might say that that an over smooth image looks worse than a noise that has some amount of noise. Okay, and therefore the kind of methods that we will see right here, they will all have to be fine tuned to an example. So in that sense, right, it will not be easy to fix the size of the filters and so on, right, and depending upon what size you choose, you might end up over filtering, under filtering, and so on, right, and therefore again, right, it comes under a subjective notion. Okay, now the point is, right, there are various types of noise, and we'll only list some of the most common kinds of noise. Some of the most common types of noise are as follows. Some of the most common types of noise are as follows. Okay, or as follows. Okay, one is additive white Gaussian noise, which I'm sure you're all familiar with. Additive white Gaussian noise, or what's called AWGN. Okay, the source is really a thermal source. Source is thermal noise arising from motion of electrons, due to motion of electrons. Motion of electrons, typically modeled as noise independent, as signal independent. Typically modeled as signal independent, right? That means it would affect the intensity of this signal at a spatial location, irrespective of the strength of the signal. Then the other kind of noise is what's called multiplicative noise. The first we saw was actually additive in nature. The other one is multiplicative, and a standard example under this is what is called the speckle noise. Speckle noise is not really common in optical imaging, but it is very common in synthetic aperture radar imaging, SAR, ultrasound, and so on. Okay, here it is very common. Okay, in these areas where also, right, there is imaging, but then of sort of, right, a different kind. Now, so okay, and this occurs, right, and the source is and the source of this noise is when occurs when when surface roughness, right? So the surface that you're imaging, surface roughness becomes comparable to the wavelength used for imaging. Okay, so kind of what this means is that there are going to be multiple scatters from, let's say, from at different points, and these could interfere in a destructive or in a kind of constructive way, leading to what we call as a speckle. Okay, this is usually modeled as signal independent. Okay, and it is multiplicative in nature. Then the other one is periodic or structured noise. Okay, this occurs because of standard fluctuations, in and around us. Let's say caused by interference, right? Electromagnetic interference, electric or electromagnetic interference, electric or electromagnetic interference, such as such as 50 hertz noise, right, which is our supply noise, 50 hertz noise, right, and this kind of noise has a regular pattern, they're actually periodic and so on, kind of single tone, right. Then the other thing that could affect you is what's called impulse noise or impulsive noise, or what's called impulse noise, right, and this is right. This is also signal independent. Okay, this impulse noise is also signal independent, but it's sparse. I mean, right? one of the key things that separates it from others is that it is sparse, signal independent, but sparse. in the sense that, right, it will not affect an image at all the spatial locations, but wherever it occurs, it will hit those locations pretty hard, right? In the sense that, but sparse, but noise strength very high, but noise very high wherever it occurs, at whatever locations, at whatever pixel locations it occurs. So it actually means that, right, you could have an image, just draw a picture, or you could have an image, right, with lots of intensities, okay, out there, but then this noise, impulse noise, could only affect it maybe at some locations, here perhaps, and here, and so on. And so it's going to be sparse, but then wherever it occurs, it will really change the intensity value there significantly. Okay, and the source of this is more right, a digital link, errors in a digital link, ADC errors. So, right, what these things mean is, for example, right, you might be kind of transmitting some information, and let's say the MSB ought to be 0, but then, right, because of transmission error or whatever, right, I mean, this becomes 1, okay, which then kind of changes the signal strength completely, okay, and independent of the signal value. Or this could be 1, and then, right, it could actually make it 0. ADC errors, in fact, it can also occur in faulty kind of displays. What this actually means is that you could have a display, okay, wherein some pixels are faulty. What that means is that these could be either a dead pixel Okay, which means that irrespective of whatever signal you input, this will always remain dark, or you could have a saturated pixel, right, which irrespective of the the input intensity or input signal strength remains a saturated pixel, right? So it also occurs because of so even if you have a display that is faulty, that kind of an image you can again model through an impulse noise. Then the other kind of thing, right, that you have to deal with is what is called photon noise. And photon noise, as we've already seen, is inherently signal dependent. Okay, and so on. Okay, this is also called short noise. Okay, so we have kind of various kinds of noise that the sources also change, right, and so on. And our goal would be to kind of look at simple algorithms, okay, that can actually mitigate the effects of these noise on images, so as to be able to enhance the visual appeal of these images. Now, we will not be looking at all of them. Okay, the ones that we will be looking at are the important ones, which is like AWGN. What kind of filters can we have for this? And then followed by periodic structured noise. This is actually simple to eliminate using what is called a notch filter. And then we'll also look at impulsive noise, photon noise, and multiplicative noise. Right, we will not be studying in this particular course, as these are beyond the scope of this course. Okay. Now, having said that, okay, let's first kind of look at what do we mean by AWGN filtering. Okay, filtering, and as we all know, right, what we would typically like to do is somebody gives me an image, right, which is just one image, right. I normally have just one image, and I would like to do some kind of filtering, right. You would have already seen that people try to use what is called a uniformly weighted filter, or what is called mean averaging, wherein you just simply average all these intensities. Suppose you want to know the intensity at this location, you want to filter the intensity here, you simply take an average of all the pixel intensities in and around its neighborhood, and and simply call that as the filtered value, and then the same thing you would do at another location, and so on. Or you could do some kind of weighted averaging, which would be some kind of a Gaussian filter, where you would probably attach more weight to the central guy, less weight to these to these neighbors, and so on. Now, it's not clear as to why, right? What is the motivation behind doing something like this? Why would it filter noise and so on, right? So in order to set the background for this, okay, we are aware of such filters, but then in order to understand, right, why these things make sense, I'm going to introduce what is called image sequence filtering first, okay, before we even look at single image filtering. So image sequence filtering. Okay, now in image sequence filtering, right, what we will assume is that we have a bunch of images of a scene, right, which we capture at rapid succession. It actually means that let us say that right, this is the first frame, this is the second frame, and then right, these are some m number of frames, right, that we capture at rapid succession. Why rapid succession? Simply because to make sure that the scene does not change, right, by the time we capture these m frames, and also, right, we can assume that all these frames are absolutely aligned, accurately aligned. I mean, they come aligned. Okay, in the sense that if there is xy, then there's also xy, it's also xy, and so on. So these pixels are all staying at at the same place across the frames. Let's call this observation as G1, let's call this observation as G2, and so on, and let's say this is GM. Now, what we know is, right, each of these frames, okay, as we observe, each of these observations has been influenced by some noise. Okay, and let's call that the GIth frame that we have observed is, let's say, the original intensity that we would like to see, which is f at x comma y, plus some noise, okay, which is eta I at x comma y, I going all the way from, let's see, 1 to m. So the idea is that, right, we like to recover f, right? Ideally, f is the one that was noise free, right? That is our clean image, and we would like to recover it from these observations, which are actually GI, going all the way from 1 to m. Now, a standard estimator for this in image sequence filtering is given by f hat of xy is equal to 1 by m summation GI of xy. Okay, I going from 1 to m. Now, because of the fact that GI is random, right? We know that GI is random because even though f is actually a deterministic quantity, see, ideally f could also be random, but in this case, just for simplicity, we'll assume that f is actually a deterministic quantity, which means it's a constant, right? and eta I is a random quantity, and therefore gi is random. And because f hat comes as an average of gi, therefore f hat, right, is random. Okay, is also random. Okay, now and in this case, this is an estimator of f. Okay, this is an estimator of f. Okay, and the idea is that when you have such an estimator, one of the things that you would like to ask is, what is expectation of f hat of xy, or what is the mean value of this estimator? Because the mean value, right, would actually give you a sense for how much you can rely on this estimator. Now, what is this value? We can actually evaluate this by doing the following. Let's say that expectation, let's call that as mu f hat of xy. Okay, let's call this as the mean value of this estimator. That will be expectation f hat of x comma y. That in turn is expectation f hat by itself is 1 by m summation gi of xy. Okay, because we know that f hat is simply this, okay, from equation 1 above. But then we know that the observation model clearly says that gi itself is nothing but f of xy plus eta I of xy. Therefore, and of course I going all the way from 1 to m. And therefore, right, what we can do is this. So this quantity inside, because f is a constant, this becomes expectation of. So you'll get m times fxy by m. Therefore, this f of xy plus 1 by m summation eta I of x comma y. Okay, this will be equal to, because of the fact that this is a constant, so this simply comes out f of xy, and because the expectation is a linear operator, we can actually push that inside summation eta I of x comma y, I going from 1 to m. And since we assume noise to be zero mean, this becomes equal to f of xy. Okay, that means the mean value of f hat is in fact f of xy. Such an estimator is called an unbiased estimator. Okay, which is actually a desirable property of an estimator. It's an unbiased estimator. Okay, that means its mean value is equal to the unknown which you're trying to estimate. If f was actually a random quantity, we would have asked for mu hat or mu f hat to be equal to expectation of f. But in this case, f is simply a deterministic quantity. That's how we have assumed it, and therefore, right, what we are simply saying is this estimator unbiased? The answer is yes. But that by itself is not enough. We also need to know how much is the variance about this value, right? Because if the variance is very high, then it means that our trust on this estimator will then be less. The other thing is, we would also like to know whether the variance, right, is a function of the number of observations or not. Because ideally, right, I would kind of tend to believe that I should have an estimator that should improve as I keep increasing the number of observations. The more observations I have, then my trust on that estimator should go up, or my trust on the estimated value should ideally go up. What is called really a consistent estimator. So we would want to ask whether this estimator, the way we have defined it, is this a consistent estimator. Right? In order to check that, what you have to look at is the variance of this guy. So let's kind of look at variance of f hat of xy, okay, which we know is simply expectation f hat of xy minus mu f hat of xy, okay, the whole square. Correct. Now this we know is expectation. Now f hat of xy is simply 1 by m summation gi of xy, okay, I equals 1 to m, minus mu f hat is f of xy, because it's an unbiased estimator, and therefore, right, what we have is this. Now if you simply examine the first quantity here, this is 1 by m summation I equals 1 to m gi of xy, which we already saw is nothing but f of xy plus 1 by m summation eta I of xy, right? We saw this already. I equal to 1 to m. Therefore, sigma square f hat of xy is going to be equal to expectation, okay, and then this minus this. So this f of xy will get knocked out, and we will get 1 by m summation eta I x comma y, I going from 1 to m the whole square. Now, since the noise realizations are assumed to be correlated, since eta I is uncorrelated with eta j, right, and they ought to be, right. Why should noise in one frame be have a correlation with noise in the other frame? Typically, they can be modeled as uncorrelated. is uncorrelated with eta j, for I not equal to j. Okay, and since noise is zero mean, what this means is that sigma square f hat of xy, it will reduce to 1 by m square. Okay, what did we have here? 1 by m square. Okay, and summation expectation eta I square of x comma y, I going from 1 to m. And assuming that the noise variance is sigma square n, this will mean you'll get m times sigma square n by m square, which is equal to sigma square n by m. Okay, where sigma square n is the variance of noise. Okay, therefore you see that the variance of this estimator is turning out to be sigma square n by m. That means as m increases, your sigma square f hat goes down at some x comma y is going down, right? So which is why this is a consistent estimator. Okay, this is a consistent estimator, which is again a desirable property. Okay, so this whole thing, right? So this image sequence filtering approach, what it is saying is you have a bunch of frames, and as long as the frames are aligned, you can simply average their frames in order to arrive at a final frame which will have noise much less than, let's say, any of these frames, and it is supposed to carry the information about the clean version of the image, which is f. It might still be affected by some amount of noise because of the fact that it's only going down as sigma square n by m. But then as you keep increasing m, you can hope to see a more and more clean version of the scene, right? Of the image of the scene. This is the idea behind image sequence filtering. Now, it is this idea that has been borrowed over to the case when you do single image filtering. The idea is exactly the same, okay, except that to what extent this will get fulfilled there remains to be seen. Okay, so when you do single image filtering, because in most cases you will have just one image, right? Seldom will you have a bunch of frames. Therefore, what you would typically want to do is what is called single image filtering, right? Therefore, you have just one image with you, not a sequence, and you would like to filter noise from this image. Okay, so as I told you, people will typically do what is called spatial averaging. So if you want to filter the noise here, you will take this intensity, multiply it by some weight, take this, all these you multiply with some weight, and then the weighted average is what you will say is the final filtered output value for this intensity. Now, the most common filters, as we have seen, are what is called a mean filter, which means that it has a filter. You have to fix the size of this filter. If you choose it to be 3 cross 3, then all the weights will be, say, 1 by 9, right? All the way. Okay, each one of these is 1 by 9, so that they all sum up to 1. The idea, right? Now when you try to relate it to the image sequence filtering problem that we saw, right? You can actually relate the two now. You'll understand the significance of doing something like this. So when you apply a 1 by 9 weight for all these pixels, what you're trying to tell is the implication or the sort of or the idea behind doing this is as follows. Because these pixels are right next to this guy spatially, so this is called local averaging. We are hoping that these original intensities of these pixels would have been roughly the same as this pixel whose filtered value you're trying to estimate. And if that is the case, then you can assume that all these have been affected by noise, again AWGN, and independent of each other. And therefore, when you average them, you would get the same kind of an effect that you got with respect, right, when you did image sequence filtering, right? So you're hoping that the more number of pixels you average, then your filtered output will have, right, that much less noise. So you might say, why stop at 3 cross 3? Why not I go to 5 cross 5, right? 1, 2, 3, 4, 5, 1, 2, 3, 4. So you've got 5 cross 5. Now your center is here. Now each weight now becomes 1 by 25, so that they all add up to 1, right? All these weights, when you add them up, you can add them up to 1. And now instead of choosing a 3 cross 3 neighborhood, you can choose a 5 cross 5 neighborhood to average. But then where is the problem there? You could have chosen the image sequence filtering, you could have arbitrarily increased m, and you could have averaged as many frames as you wanted. But here, that you cannot do because of the fact that as you increase the size of the filter, you are now hoping that a pixel here has an intensity similar to the pixel here, which may or may not hold good, and most likely it may not, because of the fact that as you go farther away from this pixel of interest, the likelihood that this guy will have the same intensity as this is going to be lesser and lesser. and therefore people will not go beyond 5 cross 5, right? 3 cross 3 or 5 cross 5 is typically common. You don't go like 7 cross 7 or 9 cross 9, because then you will end up smoothing the image, because you will start filtering out the edges, you will start smoothing the edges, and therefore, right, which is not really a thing, right, that you would like to have. Which is why I said that this is kind of subjective, because how much filtering to apply before you end up over smoothing the image, and when it becomes annoying in the sense that the image just looks too smooth. You would rather say tolerate some amount of noise than kind of tolerate an over smoothed image is a kind of subjective matter. That is why right, this comes under image enhancement, this kind of filtering. So one way to kind of avoid this is what to do is to kind of do a weighted averaging, right? Rather than give all of them equal weight, you could do a weighted averaging filter. Okay, weighted average such as simply a Gaussian filter, where you can actually pick, let's say, a Gaussian filter. You choose the sigma, whatever, right? You have, let's say, a filter that is of size 6 sigma plus 1 by 6 sigma plus 1. If that is a filter, then what you would do is at the pixel under consideration, you'll get maximum weight because it's a Gaussian. And then as you go outwards, right, you will start to give lesser and lesser weight to those pixels that are farther off. The idea being that now you will reduce the amount of smoothing, because a guy who is very different will get a less weight, and therefore, right, therefore the ability to smooth will become less, and therefore, even though you'll be filtering out noise, but then at the same time your edges will not tend to be over smoothed, because of the fact that you're going to give less weight for those pixel intensities that are farther off. Okay, this is called weighted averaging. These two filters are typically given in a more formal way. Okay, when you write them in a more formal way, okay, the way, right, you would write them is as follows. Right? Let me just write that down. So in a more formal setting, okay, you would write it as follows. So the mean filter, okay, looks like this. So G is a filter output at a pixel location P, is given as 1 by Z, where Z is a normalization constant. So a box filter, what is called P minus Q into F of Q, where F is the noisy image. So P is spatial location. It's actually a 2D vector, right, which indicates a spatial location in the filtered output. This is the filtered output, okay, which is supposed to be noise free. It won't be completely noise free. This is the noisy input at location Q. P and Q are of course spatial locations, and this average, right, is taken over a Q belonging to G. Let's say G is the spatial grid of locations. Okay, this is your Q here, and you're trying to estimate at P, intensity at P. This is P minus Q, spatial location or spatial grid, let's say. Let's call this the spatial grid. And what you have now, Z is a normalization constant, which ensures that the weights sum up to 1 for the filter. It's a normalization constant that ensures that filter weights sum to 1. That ensures that filter weights sum to 1. Sum to 1. And Z is given by Q belonging to G. Here BW P minus Q. That means you sum up all the weights. Okay, BW P minus Q. And what is this BW itself, right? So BW of some X, let's say, where X is, let's say, X1, X2. Okay, this is the form of X. Then this is equal to 1 if max of mod X1, mod X2 is less than or equal to some W, 0 otherwise. Okay. So as an example, right, if you want as an example, suppose I choose W to be equal to 2, then what this means is that, right, this Z will now be over a window of 2W plus 1 cross 2W plus 1, right? So this filter size itself is 2W plus 1 by 2W plus 1, and all those weights will be added. Okay, and so this filter size, so the BW, right, itself will be 1 over 5 cross 5 window, okay, because W is 2, so for over a 5 cross 5 window. So the filter is 5 cross 5 size, and 1 and Z, okay, because you're going to add all the weights over a 5 cross 5 window, Z will be equal to C25, so that the effective filter that you're going to apply, right, will have weights all uniform 1 by C25, right? So you'll have a 5 cross 5 filter, which will be 1 by 25, and that will multiply each of these intensities f of q within this neighborhood of 5 cross 5, right? And that will be the resultant intensity at P in the output image G. Instead, if you did a Gaussian kind of filtering, okay, which would be a weighted filtering, then this equation will get modified slightly. The modified equation, right? And all these are, of course, local averaging, right? This is also local, that is also local. We will see later what it means to do non-local averaging, but these filters are all local. These are the most common and most simple to implement, right? So what this will do is this will do G of P to be equal to 1 by Z again, right? Everything will look very similar to what we did earlier, except that now it'll involve a Gaussian instead of a box kind of function. It will be P minus Q, and then this will weight the intensity at Q in this noisy image. And all these have the same this one, okay, definitions. And the only thing is G sigma, right, of X, let's say, if I write, where X is X1, X2, okay, then this will be equal to e raised to minus X1 square plus X2 square by some 2 sigma square, right, where the sigma is the standard deviation of this filter, okay, which is again up to you to choose standard deviation of the Gaussian filter. Okay, this is something that basically we have to choose of the Gaussian filter, and e power minus provided if max of mod x1 x2 is less than or equal to w, 0 otherwise, and this w itself, right, will be where w we know is going to be 3 sigma, w will be 3 sigma, right, so that your filter size is 6 sigma plus 1 by 6 sigma plus 1. So the filter size, right? So for this, so that filter size becomes 6 sigma plus 1. Filter size is, as we all know, 6 sigma plus 1. If it is a Gaussian, right, this is what we would like the filter size to be, 6 sigma plus 1. Okay, and sigma is something that, let's say, right, we need to choose. And Z will again be sum over all the weights. Okay, G sigma of P of whatever, right? So if you want to write this as P minus Q, you can write it as P minus Q, where Q belongs to G, right? And this will be summed up over 2W plus 1, or in this case, because it's a Gaussian, so you can directly write it as, so summed over 6 sigma plus 1 plus 6 sigma plus 1 window. Okay, and therefore this will again ensure that these weights sum up to 1, except that because of the fact that you're trying to use a Gaussian filter, now more weight will be assigned to the central pixel, and then as you move away from that, you'll give lesser and lesser weight. So this is how a Gaussian filter works. These, right, both of these filters are called local filters. We will eventually see something that is going to be a powerful method, what's called non-local mean filtering. The issues with these filters is that the local filters, that they can end up smoothing out edges, okay, which is something which is undesirable. And therefore, right, recently non-local mean filters have come, which are very, very effective, right? We'll kind of talk about them subsequently.